Israel has developed one of the most deeply integrated military scientific ecosystems in the world, where nanotechnology research, autonomous systems engineering, and battlefield artificial intelligence are not treated as separate disciplines, but as converging pillars of a single national defense strategy. The country's investment in microscale and nanoscale technologies for military application is neither incidental nor recent. It traces back to formal governmental directives, sustained academic funding, and classified defense contracts that have been running in parallel with publicly disclosed research for over 2 decades. Understanding where Israel stands in nano-military development requires examining not just what has been announced, but the institutional architecture. The universities, the defense contractors, the elite military academic pipelines through which this technology is being built, tested, and deployed at scale. Israel was among the first nations to formally declare its intention to develop nanotechnology specifically for weapons applications, committing $230 million to nanoscience research with an explicitly stated military purpose, a degree of institutional transparency that most nations conducting identical programs have carefully avoided. In the years that followed that declaration, Israel's defense academic pipeline has produced nanorobotic systems capable of operating inside the human body, swarm robotics algorithms published from its top military technical university, Bioinspired nanomaterial collaborations between its premier science institute and its largest defense electronics contractor, and a publicly confirmed program to develop brain-computer interfaces that allow a single operator to direct multiple autonomous systems through neural signals alone. The convergence of these programs, molecular scale engineering, autonomous swarm behavior, AI-driven target identification, and neurotechnology represents not a collection of separate research threads, but a coherent, strategically directed trajectory toward a class of military capability that operates at a scale, speed, and level of autonomy that fundamentally changes what warfare means. The documented origin of Israel's nano-military program is unusually well-sourced for a domain where most governments maintain deliberate opacity. Under Prime Minister Ehud Olmert, the Israeli government formally authorized the establishment of a dedicated office for nanotechnology weapons development, with Deputy Prime Minister Shimon Peres assigned the specific task of selecting 15 senior thinkers drawn from the security establishment, the technology sector, and academia to lead the initiative. The $230 million budget, allocated over 5 years, made nanotechnology one of the highest-funded research domains in the country, and the stated objectives were operationally specific, developing responses to threats ranging from short-range rockets and suicide attacks to long-range missiles and unconventional weaponry. What distinguishes this declaration is its candor. While the United States, China, Russia, and other advanced military powers have all pursued comparable programs under the broad vocabulary of defense research and dual-use technology, Israel was identified in scientific literature as the first country to publicly state that. Nanotechnology was being developed for weapons. The institutional significance of this is considerable. It established nanotechnology not as a peripheral curiosity, but as a formal strategic priority, with dedicated funding, dedicated personnel, and a direct mandate from the highest levels of civilian government. The Technion, Israel Institute of Technology in Haifa, functions not merely as an academic institution, but as what analysts have described as the technological foundation of Israel's entire defense manufacturing sector. The statistical relationship between the Technion and the Israeli military-industrial complex is without meaningful parallel among democratic nations. Approximately 80% of engineering graduates from the institution enter careers directly connected to defense research or defense manufacturing. This is not a coincidence of economic circumstance, but the result of deliberate structural design. Programs such as Talpiot and Havitzalat identify the highest performing students in Israel's mandatory military service system, place them in accelerated academic tracks at institutions including the Technion, and provide a seamless institutional pathway from graduate-level research directly into classified defense programs at organizations including Rafael Advanced Defense Systems and Israel Aerospace Industries. In 2024, Technion researchers published peer-reviewed work on cooperative defense strategies employing swarms of autonomous agents equipped with sensor arrays designed to provide guaranteed detection coverage against mobile invaders attempting to penetrate a guarded perimeter, research that sits precisely at the intersection of swarm robotics and perimeter defense, and which carries direct applications in the design of autonomous nanoscale and microscale surveillance systems for military deployment. The Weizmann Institute of Science in Rehovot, regarded as Israel's most distinguished research institution and described in Israeli press as the country's technological backbone, occupies a position of significant complexity in the nano-military landscape. In a collaboration that was publicly announced before being removed from the Institute's official website, Weizmann entered into a formal research partnership with Elbit Systems, Israel's largest defense electronics company, to develop what the announcement described as groundbreaking bioinspired materials for defense applications (ESPRADES). Bioinspired materials research at the nanoscale involves the systematic study of structural and functional properties found in biological organisms, the tensile mechanics of spider silk, the adhesion chemistry of muscle proteins, the hierarchical architecture of bone, and the engineering of synthetic analogs that replicate or exceed those properties for applications in protection, concealment, sensor design, or weapons delivery. The Weizmann Institute maintains documented collaborative relationships with both Elbit Systems and Rafael, contributing to programs encompassing artificial intelligence for combat data analysis, unmanned aerial vehicle systems, electronic warfare platforms, encrypted communications, and alternative navigation technologies. The dual-use character of bioinspired nanomaterial research, where a surface coating engineered to improve drug delivery and one engineered to improve the penetration resistance of a weapon's casing may share identical underlying chemistry, makes the boundary between civilian science and military application in this context genuinely indistinct rather than merely ambiguous. One of the most technically specific data points in the Israeli nanobot record is the device developed jointly by the Technion and the College of Judea and Samaria under the direction of Professor Moshe Shoham, a functional nanobot measuring 1 millimeter in diameter, equipped with articulated appendages enabling it to maintain positional stability inside tubular biological structures of varying diameters, and to resist displacement by blood flow. The device was developed with an explicitly medical application in mind, enabling minimally invasive surgical procedures with precision levels unachievable by conventional instrumentation. The engineering challenge it solves: navigating an autonomous device through a fluid-filled biological environment, maintaining position against dynamic resistance, and delivering a payload to a specific anatomical location is, at the level of physical principles, identical to the challenge of delivering a pharmacological, chemical, or biological payload to a targeted human subject through a concealed internal pathway. The distinction between a medical nanobot and a weaponized nanobot is not a distinction of engineering architecture, but of programming objective and payload specification. Israel's demonstrated capability to construct functional nanorobots with autonomous navigation and payload delivery functions in biological environments means the technical foundation for a militarized variant exists as an engineering derivation, not as a theoretical aspiration, requiring fundamental scientific breakthroughs not yet achieved. Israel's Defense Research and Development Directorate, DDR&D, has developed and is actively deploying what it designates the Seek and Strike Autonomous Drone Swarm System, a platform that operates not as a collection of individually directed units, but as a networked collective sharing real-time data, adapting cooperatively to battlefield conditions, and executing coordinated strike or surveillance missions with minimal human oversight. The system is equipped with advanced intelligence, surveillance and reconnaissance capabilities, terrain dominance functions, and strike payloads configured for both open terrain and urban combat environments. Full integration into IDF combat brigades was projected for 2026, reflecting a deliberate institutional shift away from human-operated platforms toward autonomous battlefield systems as a primary rather than supplementary capability. The significance of this program to the broader nano-military question is architectural. The swarm intelligence algorithms, the inter-unit communication protocols, the cooperative target identification logic, and the autonomous decision-making frameworks developed for the seek and strike system are directly scalable downward in physical size. A swarm of meter-scale drones operating on cooperative autonomous principles is, in terms of the governing software and communication architecture, the same system as a swarm of centimeter-scale or millimeter-scale devices. The engineering difference is miniaturization, not conceptual reinvention. The June 2025 Israeli operation, codenamed Rising Lion, provided the first large-scale operational demonstration of Israel's autonomous swarm doctrine in a contested, high-intensity military environment. According to analysis published by the Center for Strategic and International Studies, the operation opened with swarms of small explosive drones that Israeli forces had reportedly pre-positioned inside Iranian territory months in advance, deploying against air defense radar installations and communications nodes in a coordinated sequence designed to suppress defensive systems and redirect Iranian attention before the main strike package, over 200 F-35 aircraft, conducted precision strikes against more than 100 military and nuclear targets across Iran. The operational architecture of this engagement is analytically significant beyond its immediate strategic context. It demonstrated that Israel has the capability to pre-position autonomous lethal systems in adversary territory covertly to coordinate their activation with precision timing from remote command centers, and to integrate swarm-executed preparatory strikes with conventional air operations in a unified battle plan. The pre-positioning G element, placing autonomous systems inside enemy territory well in advance of their activation, is a doctrine with direct implications for nanotechnology. A system small enough to be undetectable during insertion could be positioned with far greater concealment and at far lower risk than the systems deployed in Operation Rising Lion. The 2025 Israel-Iran conflict has been characterized by defense analysts as the first large-scale military engagement in which artificial intelligence was not merely integrated as a supplementary tool, but functioned as an indispensable operational component across intelligence collection, target identification, and strike execution. AI systems in this conflict performed real-time data fusion across multiple theaters of operation, prioritized threat sequencing, and generated strike recommendations at a tempo that would have been operationally inaccessible to human analysts working within conventional intelligence timelines. The governing doctrinal framework, maintained by Israel and its allies throughout, was described as human on the loop, rather than human in the loop, a distinction with substantial implications. In a human in the loop system, a human operator must authorize each individual action. In a human on the loop system, the AI executes autonomously within pre-authorized parameters, with human oversight exercised at the level of policy rather than individual decision. This doctrinal posture, AI autonomy within policy constraints rather than per-action human approval, is the precise framework that would govern a nano-military system. Swarms of nanoscale devices executing autonomous targeting and delivery functions within pre-programmed operational boundaries, with human authorization occurring at the mission planning stage rather than the individual action stage. In February 2026, Dr. Alona Barnea, director of the Nanotechnology Division at Israel's Defense Ministry Research and Development Directorate, publicly confirmed at a technology conference in Tel Aviv that Israel is actively developing brain-computer interface systems designed to allow a single military operator to control multiple unmanned systems through neural signals, including eye movement, hand motion, and direct brain activity alone. The operational concept articulated by Barnea involves a single BCI-equipped operator managing an entire defensive swarm, directing multiple autonomous systems across a complex threat environment as fluidly and intuitively as the operator's own cognitive processing. The strategic logic of this program becomes particularly significant when considered in relation to nanoscale systems. The human sensory and motor bandwidth available for conventional interface-based control is a limiting factor on the number and operational complexity of autonomous systems a single operator can manage. A direct neural interface eliminates this bandwidth constraint, making it theoretically possible for one operator to coordinate hundreds or thousands of autonomous nanoscale devices simultaneously. Israel's active development of BCI technology, alongside its established competencies in swarm algorithms, nanoscale robotics, and AI-driven target identification, indicates a trajectory toward an integrated operational architecture in which nano-military systems are neither theoretically imagined nor distantly projected, but structurally anticipated in the command and control frameworks now being engineered. Prime Minister Netanyahu's announcement of a $350 billion defense modernization budget to be deployed over 10 years with explicit emphasis on technological advancement and Israeli weapons independence provides the financial architecture within which nano-military research and development is being accelerated. The IDF's concurrent establishment of a dedicated directorate for AI and autonomy, charged with spearheading research and force building across artificial intelligence and autonomous systems, institutionalizes nano-military capability development within the formal military command structure rather than leaving it as a peripheral academic or contractor-level initiative. The emphasis on weapons independence is analytically relevant. Israel's experience of supply chain disruptions and the geopolitical constraints that periodically affect its access to foreign defense technology have created a structural preference for developing domestically produced military systems that do not depend on foreign supplier relationships. Nanotechnology-based weapon systems, which require highly specialized domestic scientific and manufacturing infrastructure and are not commercially available from foreign suppliers, are precisely the category of military capability that Israel's independence doctrine would prioritize for internal development. The scale of the budget, combined with the IDF's explicit institutional commitment to autonomous systems across all domains of military operation, provides both the financial resources and the organizational mandate for nano-military programs to advance from laboratory-level research to field-deployable capability within the budget's 10-year horizon. An accurate assessment of Israel's nano-military development requires distinguishing between what is publicly confirmed, what is structurally implied by the documented institutional architecture, and what remains genuinely uncertain. What is confirmed? Israel has functional nanorobots operating inside biological environments. It has operational swarm systems with autonomous, targeting, and cooperative behavior. It has active programs in Bioinspired nanomaterials for defense, AI-driven autonomous combat operations at scale, and brain-computer interface control of unmanned systems. And it has the formal governmental mandate, the dedicated budget, and the integrated academic military pipeline to advance all of these capabilities simultaneously. What is structurally implied? The convergence of these separately confirmed programs, nanoscale robotics, swarm algorithms, AI targeting, BCI control, along a single operational trajectory suggests that the Israeli defense establishment is not developing these capabilities in isolation, but as components of an integrated nanomilitary architecture whose full parameters remain classified. What is genuinely uncertain? The current state of specifically weaponized nanoscale systems, devices small enough to be defined as true nanobots, sub 100 nanometer scale, with autonomous lethal function, remains outside the documented public record, as would be expected for the most sensitive tier of any advanced military program. The institutional evidence does not support the conclusion that Israel possesses deployable weaponized nanobots at true nanoscale today. It does support the conclusion that Israel is among the nations most systematically and deliberately positioned to develop them.